a bit about what Diana's been up to.
Hi everyone, I'm Diana and I'm Banana Plug, and I'm going to be a senior at the University of California, Santa Cruz. And this summer I worked with Kevin Mahan, who's a structural geologist at CU. And so this summer we're studying the development of deep crustal shear zones and their implications for seismic anisotropy. The shear is made up of the crust and the upper mantle, and what we're going to be studying is the lower crust. But at about 15 kilometers in depth into the Earth, you have this brittle, ductile transition where rocks start to behave differently. So at above 15 kilometers, rocks behave as if they do on the surface of the Earth. So they just break and they crack. But at below 15 kilometers is when they start to squish and recrystallize and deform. So within this ductile zone, there are these shear zones can develop. And therefore, that's the mechanism for deforming rocks. But more specifically, I'm studying rocks from Gallatin Canyon, Montana. So here's North America right here, and this is Idaho and Wyoming. And a zoom in of this red box is my sample location, which is within the Precambrian basement, with pressures of about 1 gigapascals, which is about 35 kilometers, and temperatures of 700 to 800 Celsius, so it's pretty hot. But what's really special about my rocks is that they have these centimeter shear zones, seen here. So seeing and having these centimeter scale shear zones allows us to study such a common process more in depth because they're tiny and you don't have to, go from 1 kilometer to, you don't have to travel a kilometer to see this common process. So it allows this transition between the undeformed protolith to the highly deformed myelinite, ultramyelinite. So an undeformed rock is relatively isotropic, so the minerals are randomly oriented, and so if you shoot waves, an average velocity. But as strain and deformation increases, minerals within the rock align themselves and have a lattice preferred orientation. And this is when seismic anisotropy is a difference in wave velocities as a function of direction of propagation. So this is why it's important to study this transition, because ultimately we can understand the development and evolution of seismic anisotropy. So when I talk about a transition, and I use the word protolith and ultramyelinite, a protolith just means that the rock is undeformed, and a protomyelinite is where less than 50% of the original minerals have recrystallized. And then in the final stages, you get an ultramyelinite, where a majority of the minerals have recrystallized and reoriented themselves. So just as a roadmap for now, I'm going to be here for 3 more weeks. So we've only touched base on a lot of the methods of some field work. We've done some field work, some sample characterization, and doing some seismic anisotropy. So I'm just going to be showing you guys some preliminary results of each method. So I was fortunate enough to go out into the field for a week in Gallatin Canyon, Montana. But what's really unique about my rocks is the fact that there are these centimeter scaled shear zones and that they have a common lithology of the deep crust. So it's not so much important that they're in Montana, even though Montana is beautiful. It's the fact that you have these really cool features. But I learned, I was there for a week. I looked at my rocks for 2 days, but I was there for a week, and I learned a lot of important field skills because I haven't taken structural geology yet, so that was awesome. So to begin, I began by doing some petrographic techniques and microstructural analysis just to characterize this transition. And I honestly spent quite some time just looking at the thin section and trying to figure out areas were representative of that stage between a protolith and an ultramyelinite. So some awesome observations that we've made so far is that in the protolith, the undeformed metamorphic protolith, The minerals you can see are randomly oriented and that sort of igneous-like textures. And then once you get to the protomyelinite, minerals are, you see the beginning stages of minerals start to align themselves. So you see these pyroxene cores, orthopyroxene and clinopyroxene, and you see hornblende surrounding them. And by the time you get to the myelinite, minerals have a preferred orientation, so we expect some kind of anisotropy in that area. But what's really cool is that once you get to the ultramyelinite, you have complete alignment of these minerals, and either they've recrystallized into this orientation or they've rotated themselves into the shear plane. And the shear plane being this way. I have a bunch of arrows to help you orient yourself relative to the shear plane. So keep an eye on this. Awesome. So in order to quantify the previous observations, we did some quantitative data using scanning electron microprobe data. And more specifically, we've got some ChemScan data and some EBSD data. So far, we've only done it on the ultramyelinite zone. So ChemScan data allows us to obtain modal proportions, so percentages of each area, percentages of the minerals in each area. And electron backscatter diffraction data allows us to, but they also give us the orientation and understanding seismic activity. So far, data on the ultramyelinite zone. This guy, or that guy, because this is really awesome. And so far, the EBC data has showed us that what we expected to be plagioclase is actually scapholite. And we don't really know what to do with that yet, so we're just pretending it's plage. But, but from this EBSD data, we've come up with, we've made some lower hemisphere stereographic projections, and the main thing to get away from it is that here's the foliation plane in hornblende, for hornblende, looking at the C-axis. And you can see that hornblende has a preferred orientation, exactly what we see here. So I thought that was freaking awesome. But so from the ChemScan data, like I told you guys, we were able to get these modal proportions of each mineral. And some important things is that you have no garnet or hornblende in the protolith. But as strain increases and deformation increases, you have an exponential, a huge increase in hornblende, and garnet appears. And we expect that because garnet is a metamorphic mineral. But another thing to note is that plage and quartz stay relatively constant, and pyroxene significantly decreases. And lastly, after collecting EBSD data, we hope to do some seismic anisotropy calculations using the main price anisotropy program, which requires EBSD data, and I've only done it on the ultramyelinite zone. Lower hemisphere stereographic projection of the ultramyelinite zone. And again, what you can see here is that here's the foliation plane, and if you've got a wave in this direction, waves will travel faster than shooting a wave to this direction, and it's oblique plane, which is something we see all throughout. So in conclusion, studying these centimeter shear zones allows us to analyze this common process way more in depth, and thus study this transition between a protolith to the ultramyelinite. And by studying this structure, hopefully we can so anisotropy is fundamental. Studying the seismic anisotropy in these centimeter scaled shear zones is ultimately needed to understand deep structure. And so the next few weeks, I'm going to be doing more microstructural analysis and more EBSD data collection and more pumping out anisotropy calculations. I'd like to thank Kaylee Condit, which is Kevin's PhD student, because she helped me survive out in the field. And I'd like to thank Kevin and Vera, who helped me with the seismic anisotropy portion, and Fran, my writing mentor, and Peter, and everyone who supported me this far. And I'm excited to continue this project.
Question?
Since these rocks are more stable at greater depths, do you ever have to worry, since they've been uplifted to the surface, do you ever have to worry about maybe back metamorphism or overprinting?
Oh yeah, there's so many different metamorphic processes going on, and I wish I could tell you more, but I just know that like my rock is really cool because so many things are happening at in one rock. Yeah, I'm sure there are though.
How anisotropic is the most nefariously aligned hornblende? Is it like a particularly?
How isotropic?
Or sorry, anisotropic.
Is the ultramyelinite?
No, is hornblende as a mineral like the most?
Well, so hornblende and mica and quartz all are huge contributors in seismic anisotropy of a rock, and that's as much as I know so far. So that's why I'm focusing on quartz and hornblende. Oh, yeah. So in here we get, so this was like a free run, like first trial, and we got 2% anisotropy in the ultramyelinite, which is not something we expected. We expected something like 6%, because all the minerals have aligned themselves in a preferred orientation already. So I don't know if I answered your question, but I kind of just talked. Sorry.
You probably maybe mentioned this. What type of, are you working in like a gneiss or a schist, or what's going on in this? What type of rock is?
I'm working on a metamorphosed gabbro.
Got it.
I don't know. I don't think I mentioned that.
Got it.
All right, we actually have a question from the WebEx. It says, well done, Diana. Beautiful graphics. Any idea of the pressure and temperature at which these shear zones form? This is from Julian.
Didn't I say that in the, about 1 gigapascals, Julian? Which is like 35 kilometers in depth. Is that okay?
Oh, Julian can now speak out loud.
Oh, hi. Sorry. Well, thank you. Yeah, I was just wondering if this could be something that would occur during the exhumation, so at lower pressure.
Oh, that's an interesting question, Julian. I am not really sure. You can ask Kevin.
All right. Well, maybe we'll see that in the next 3 weeks. Thanks anyway.
Yeah, we'll find out, and we'll let you know.
Hope so.
Okay.
Well, let's thank Diana again.